In this unit, we will look at the wafers and materials used for silicon photonics waveguides. The waveguides commonly used for silicon photonics are termed silicon-on-insulator. These are commonly used in electronics for high-performance circuits. The typical 200 mm or 8-inch wafer consists of about 725 microns of silicon substrate, 2 microns of oxide, known as buried oxide, or box, and 220 nanometers of crystalline silicon. It is on top of the crystalline silicon layer that waveguides and devices are defined. Hence, the material properties of this silicon are important for designing optical devices. The examples presented are based on a top silicon thickness of 220 nanometers, which has been used since before 2003. The 220 nanometer thickness has become a standard used particularly by multi-project wafer foundries and foundry service providers such as IMEC, LEDI, and IME in Singapore. Other thicknesses are also in use, for example, Luxtera, Katura, and Scorpius. It should be noted that the optimal thickness is application dependent, but that 220 nanometers has been a highly used standard. The wafers are fabricated using thermal oxidation, smart cut technology to create a thin layer of silicon, and wafer bonding. Let's focus on the material properties of the SOI wafers. The top layer is crystalline silicon and ranges from 50 nanometers to 3 microns. The typical standard for multi-project wafers is 220 nanometers. The waveguide is surrounded by silicon dioxide. Below is the buried oxide layer, and above is the cladding, which is deposited after the waveguides are fabricated. Let's discuss the index of refraction. The phase velocity is the speed at which a monochromatic beam of light will travel. It is determined by c, the speed of light in vacuum, divided by the index of refraction. Silicon is approximately 3.47, while the oxide is approximately 1.44. Both of these effective indices are wavelength and temperature dependent. As we can see, silicon has a much stronger wavelength and temperature dependence. These are plots for the index of refraction for silicon and silicon dioxide. The data points are from Palek's Handbook of Optical Constants of Solids. The curves are fits to this data using a Lorentz model. It is important to smooth this data using a fitting procedure since there are few points in this data set and the data has experimental uncertainty. As we can see, silicon dioxide has a weak wavelength dependence. Also, as mentioned, the temperature dependence is weak and is an order of magnitude smaller than silicon. Finally, most of the light is guided inside the silicon. Thus, we generally focus our attention on an accurate silicon model, and we can assume a constant index for the silicon dioxide. Similar to the index of refraction, which is related to the phase velocity, the group index is related to the group velocity. The group velocity is the velocity at which the overall shape of the wave propagates through space. Here we are speaking about pulses of light, or a beam consisting of multiple wavelengths. An optical pulse actually consists of numerous components at slightly different wavelengths. Each of these experience a different index of refraction, hence each travels at a different speed. This leads to the pulse traveling at a different speed than the individual phases of each wavelength component. The group index can be found if we know the wavelength dependence of the index of refraction, namely dn d lambda. We will see that when we design optical circuits, for example the interferometer, that the response of the circuit is dependent on the group index. In fact, you will see that it is easy to measure the group index from the optical circuit's behavior. However, it is challenging to measure the index of refraction directly. We can also consider higher order dispersion terms by taking further derivatives. This allows us to consider group velocity dispersion, which describes how a pulse spreads in an optical fiber, for example. If we know the mathematical expression for the index of refraction, we can calculate the group index. The MATLAB code shown here creates a plot of both the refractive index and the group index of silicon. This is the result. As you can see, the group index is higher than the refractive index. This is due to the negative slope of the refractive index versus wavelength. Since the speed of a pulse is related to the group index, This means that information always travels slower than the phase velocity as described by the refractive index. What we see here is known as material dispersion. This is one contribution to the total dispersion of the waveguide that we're interested in understanding. This contribution is not the dominant one, but cannot be ignored. One important consideration when performing simulations is that your material models need to be consistent throughout your different simulations. The way I've approached this is by using a Lorentz equation to fit the materials. I use the same material model throughout all my simulations, particularly in the Silicon Photonics design textbook. You may choose a different set of material parameters, but be sure to be consistent when performing comparisons, for example, with others.